wanted to take 5 minutes to finish up what we were talking about in class before the fire drill happened. And that is that instantaneous velocity can be computed on graphs as well as from a table of values. If you think about average velocity, V average equals delta x over delta t, then you can see that if I have 2 points, 2 times A and B that define the time interval, A and B right here, then the average velocity between the two is exactly equal to the slope of the line connecting the 2 points on the curve. Because, as you know, slope is rise over run, and this slope down here would be a delta t, and this length right here, the run, would be delta t, and this height right here would be delta x. And so we call that a secant line because that secant line cuts through the curve, just like that. And secant is from the Latin word sectare, which means to cut, from which we also get scissors and dissect and other such words. Well, remember in class that we said that the instantaneous velocity v is the limit as delta t goes to 0 of delta x over delta t. What does that mean on this graph here? Well, let me pick a point A, and what I'd like to do is to estimate the instantaneous velocity off of the graph. And so I'll go out a small time interval, maybe to right here, and I'll do a secant line for myself, and the slope of that secant line is the average velocity here. And if I let delta t now shrink to 0, then that means that my time out here is coming closer and closer to A, so that my 2 points, the beginning point and the end point, are merging into one single point. And at that point, we have a line that touches the graph, not very well, there we go, at a single point, and we call that a tangent line, from the Latin word tangere, to touch. So if I want to estimate the velocity at a single point, the method is very simple. I simply go to that point, I draw myself a tangent line touching the curve there, and then I estimate the slope of that tangent line using the usual rise over run method. We can say a little bit more here, because just by looking at the shape of the curve, we can at least get an indication of the sign of the velocity. Notice that for all the times between 0 and t1, my position is going up. It is increasing. And as a result, when I put a tangent line to the curve at any point between t0 and t1, and I just picked one point at random, then my line will be a rising line. It will have a positive slope. So I don't even need to measure that slope to see that my increasing position implies that my slope, my velocity, will be a positive number. And likewise, for t's between t1 and t2, you can see that the position from here to here is going down. And as a result, when I put a tangent line to that curve, that tangent line will have a negative slope for any time between t1 and t2. So a decreasing x, which is what we have here, means that my velocity is going to be negative. And guess what happens right at the top? You probably guessed it. Right at the top right here, my tangent line is horizontal, and therefore it has a slope of 0. Right at t1, which is the maximum on the curve, my velocity is equal to 0. So that gives you a way to estimate slopes just the signs of the slopes simply by looking at the direction of the curve. If the curve is going up, it will have a positive slope. If it is going down, it will have a negative slope. And if it is right at the top or right at the bottom, and it is in the process of changing from going up to going down or vice versa, then it will have zero slope. That's all.